Hello and welcome. This is class 7. I again am Dennis Doverspike, in case you've forgotten or don't know. And in class 7, we're going to in a sense take a step back, one or two steps back. We're going to discuss really mediation, and we'll discuss mediation within the process model. So we're going to discuss how to do mediation or mediation analysis. And specifically, in discussing mediation, we're going to look at the Hayes process model. Now, when I designed this class at the time, Hayes had still not created an official process piece of software or program for use on R. So at the time I created this class, process was not available yet on R. My understanding is process is now available on R in a beta version. It won't be available in a full version or a non-beta version until later in the spring, but you can now get it in a beta version for R. We're using process through SPSS, and so does field. So you can add on process to SPSS. Once you add it on, it appears right in the menu, so it's really easy to use. It does help if you're going to use process to read Hayes's books. So it does help to go out and get to Hayes's book and read his books. If for no other reason, he lists all these different models he has, which get quite complex. Okay, but anyway, we'll be talking about the analyzing for mediation and the process model or the process program or the process software. Okay, what is mediation? Well, mediation is really a great thing, really, if you're a student or a graduate student, because it's going to help you do, I think, your thesis or dissertation. I tell students who are interested in doing research or an original thesis or dissertation, the best way is to think of two important or practical variables you might be interested in. We'll label them X and Y. Now, just because you're interested in X and Y and everybody else is interested in X and Y doesn't mean a dissertation committee is going to approve your dissertation. And it doesn't mean that it'll get published. Because unfortunately, in the minds of many, theses and dissertations and even getting articles published in journals doesn't require solving practical problems. It involves having a theory and testing that theory. But there's an easy way to build theories. And the way to build theories is to have variables that you add as mediators or moderators. Now, again, we've already discussed moderators, and we'll be discussing moderators next week in class 8. But in this class, we'll be discussing mediators. So mediation is really trying to make a causal statement, often out of non-causal data or out of non-experiments. So one of the uses of mediation is to try to make causal statements in those situations in which you either have archival data or you have survey data, but you haven't done either a true or a quasi-experiment. Now, of course, we can argue as to whether you can really then imply cause or not, but that's a different issue and one we can discuss, but it's a different issue. Now, of course, you can also use mediators. As a matter of fact, you might argue it's where they'd be particularly valuable when you have manipulated the independent variable. So we can always look at mediators with an actual true experiment with a manipulated independent variable as well. So anyway, mediation tries to make causal statements. It's a way of building theories. It seeks to identify and explains the mechanism or process that underlies an observed relationship between an independent variable and a dependent variable via the inclusion of a third hypothetical variable known as a mediator variable. Also a mediating variable, an intermediary variable, or intervening variable. Geez, looks like I'm having trouble talking today. Rather than a direct causal relationship between the independent variable and the dependent variable, a mediation model proposes that the independent variable influences the non-observable mediator variable, which in turn influences the dependent variable. Of course, to study it, we have to make that mediator variable then observable. So even though we say non-observable here, to study the process, the mediator variable has to become observable or measured. So here's one sort of typical mediation model. It's one of the areas of psychology where there's really a lack of theory. There's a theory called stereotype threat. If you're familiar with the theory, it argues that minorities often underperform on tests because they feel that taking the test is a challenge to their group. That's probably the prime theory, that in taking the test, they're representing their group. And if they do poorly, it's going to reflect poorly on their whole group. And so minorities feel this stereotype threat, and it reduces their test performance. And in particular, they're going to experience when either the test medium or the test format or the test content is one traditionally associated with lower performance by their group. And so frequently we're actually manipulating the independent variable. And there is quite a bit of research that even if the effect is small, we can constantly replicate a relationship between certain test media or content and diminished test performance for minorities. Now, of course, the question is why or how does that occur? Now, one explanation might be test anxiety. So if I wanted to develop a thesis or dissertation and test this idea, I start out, I have my independent variable test medium. For example, we have a test, and in one case we describe it as an intelligence test, and in another case we just describe it as a problem-solving test. And then we have test performance, which of course is how we score on the test. And we know, or at least hope, that in our study test medium will affect test performance. And now what we do is insert this mediating variable that we also measure. And so, for example, maybe we give a test of test anxiety because we're arguing that the mediator between test medium and test performance is test anxiety. Here would be another example. I've given this before. This is a police incident with a veteran. We argue that when a police officer sees a veteran involved in an incident, they're going to have to make a decision as to whether to use force, whether to arrest the person. So they're going to have to make various decisions. Well, what's the mediator? Well, we might argue that the mediator is perceived danger. So now we can have a model. We can manipulate what kind of an incident the veteran is involved in. We can then measure the mediator, perceived danger. And then we measure, of course, the dependent variable. What kind of decision does the police officer make about an arrest or the use of force? And again, we mentioned the Fishbein and Eisen model before. This is really a classic mediator model because we have these sort of independent variables, and they all influence intent, which then influences behavior. So in this classic Fishbein and Eisen model, the mediator is our intent. Okay, there's other ways to do mediation analysis. We don't really need to use process. We could just use hierarchical regression. But we're going to use process because one, field uses it, and two, that's what we're teaching right now, the use of process. And again, process is a technique, a routine, a program developed by Hayes for the analysis of mediation and moderation. So again, mediation, now this is slides from Andy Field. Mediation refers to a situation when the relationship between a predicted variable and an outcome variable can be explained by the relationship to a third variable, which we call the mediator. So our simple relationship again would be predictor to outcome, and our effect we label C. Our mediated relationship is predictor to outcome. And now we have two effects, though. We have an indirect effect and a direct effect. The direct effect we're going to indicate by C prime. The indirect effect is the effect of the predictor to the mediator and the mediator to the outcome. So the indirect effect is predictor to mediator, mediator to outcome. That's the indirect effect. The direct effect is predictor directly to the outcome. And so we're going to see to what extent the mediator explains the relationship between the predictor and the outcome. Of course, the most interesting thing would be, right, if we had full mediation. That would be really interesting. If there's no direct effect, if the whole effect is indirect, that is, the only effect of the predictor on the outcome is through this mediator, through the A path and the B path, that would really be interesting. That doesn't always happen, or maybe even usually happen. Usually, we end up with an indirect effect and a direct effect. Now, another sort of interesting aspect of this would be, what if there is no predictor-outcome relationship? Can we still have a mediated relationship? This is the topic of a lot of debate. I hope some of the articles I assigned discuss this. If not, we'll discuss it. But there's debate in the field. There's a debate in the field. Some experts would argue if there's no relationship between the predictor and the outcome, you can't have a mediated relationship. Other people would argue even if there's not a simple relationship, you can still have a mediated relationship. So there's a little bit of dispute there. I would argue it probably partially depends on what kind of data you have. I mean, if you're manipulating your predictor and it has no effect on the outcome, only an effect on the mediator, then I have to question what that's really telling you. That is, if you've manipulated the predictor. On the other hand, if the predictor is not one that's manipulated, if you're just using, for example, survey data here, then maybe the fact that there's no direct relationship, but there is a mediator, or no simple relationship, but there is a mediator or indirect effect relationship, does in fact tell you something. So we'll probably again be discussing that more when we look at the articles, hopefully. But it's just a topic to be aware of. Okay, probably the study of mediation started with Barron and Kenny, 1986. And I believe I've given you some readings from Barron and Kenny. And Barron and Kenny argue that mediation can be tested through 3 regression models: predicting the outcome from the predictor variable, predicting the mediator from the predictor variable, and predicting the outcome from both the predictor variable and the mediator. And then you can use that information to get your paths. Barron and Kenny also argue there's 4 conditions of mediation. The predictor, and so you'll note, this is what we were just talking about. Barron and Kenny say the predictor must significantly predict the outcome variable. So that's number 1 there. Now, as I said, since Barron and Kenny, not everyone agrees with that. The predictor must significantly predict the mediator. Number 3, the mediator must significantly predict the outcome variable. And then 4, the predictor variable must predict the outcome variable less strongly in model 3 than in model 1. So the predictor variable must predict the outcome variable less strongly in model 3 than in model 1. So when we get to model 3, when we're partialing out the mediator, the effect of the predictor must be lower in model 3 than in model 1, or condition 3 than condition 1, if you understand that, I hope. Okay, there's a number of limitations, though, to Barron and Kenny's approach. One of the major limitations is how much of a reduction in the relationship between the predictor and outcome is necessary to infer mediation. So this is sort of what I talked about before. You don't always get full mediation. So if you're not getting full mediation, how much of a reduction in the relationship between the predictor and outcome is necessary to say there's mediation going on? People tend to look for a change in significance, which can lead to the all or nothing thinking that p-values encourage. That's saying that's a problem. There is also something called a Sobel test. The Sobel test is from 1982. It's an alternative used to estimate the indirect effect and its significance. Basically, if the Sobel test is significant, there is significant mediation. One of the problems, of course, is significance test depends upon sample size, but, that's always true. To me, that's not a huge problem because we know that's always true, that significance tests are going to depend upon sample size. It's probably best to read Field to understand these next couple slides. I'll try to explain them, but, Field has a lot more room to write text explaining these various effects. And also, Field sort of starts off by saying you probably don't need any of these effect sizes because probably the best indicator of the effects are the b-values, the regression weights. So Field does start out by saying that probably the best thing to do is just look at the b-values. But then he goes on to still give these other effects. And some of them have names and others do not. But he starts with the indirect effect, where the indirect effect as an effect size is simply A times B. And if you go back, again, while I'm recording these, I can't go back and show you a past slide. But if we went back, or if you go back to the slide or in the book where it shows you the model, A is the path from the predictor to the mediator. B is the path from the mediator to the outcome. So he's saying the indirect effect is equal to A times B. There's also an indirect effect partially standardized, which equals A times B divided by the standard deviation of the outcome. Then there's an indirect effect standardized, which is A times B divided by the standard deviation of the outcome times the standard deviation of the predictor. And I think he gives that one a name. Let me look here. And it's, yes, he calls it the index of mediation. So he calls that the index of mediation. So these exist. He discusses them in the book. You're not going to be calculating them anyway. You're going to be using process. But I guess it's useful to know what they are and what they mean. We can then also calculate additional effect sizes. So I don't know that these have names, and I don't think I'm looking at Field. I'm sort of treating it like a Bible right now and looking at it as our Bible statistics, and I'm looking at it to see if Field gives them any names, and I don't see that he does, and I don't know of names for them, but we have what he calls P sub m, and P sub m is just AB divided by C. Now, we just discussed what A and B are, and of course, C, again, is that original simple relationship between the predictor and outcome. We then have R sub m, which is AB divided by C prime, where C prime is the estimate of the remaining direct effect between the predictor and the outcome. And then we have this down here, if I still have my pointer, we have our regression estimate of the influence due to mediation. So we have this regression estimate. And again, if you'd like further explanation as to what this is and what it means, go to page 372 in the Field textbook. If you have the North American version, and you'll see an extended discussion of what exactly this means. All right, we're going to return to our COVID problem. Now, for this COVID problem, I decided to do something a little different to look at mediation. and I have trouble saying this word, an epidemiologist, is that correct? Don't judge me too harshly. An epidemiologist believes that the effect of density on deaths, so the population density on deaths, is mediated by air pollution. Okay, so we're going to add in air pollution. Now, I have a little note here that all the other data in this database are real except for air pollution. I made that up, but that's no longer true. This is the kind of service I deliver to you. I was unhappy with having made up any data. So I actually went out and got the air pollution data for each state. Now, what this air pollution data is, it's really a rating of how healthy the air is. And the lower the number, the healthier the air, the less air pollution. So a lower number is less air pollution, but it's a rating of how much air pollution there is. So we're going to do a COVID problem. We want to see if the effect of density on COVID deaths, population density on COVID deaths, is mediated by air pollution. I'm coming to you to interrupt this TV show to just make a correction. So just so you have it correct as we go through these slides, I want you to know or remember that despite what I say, death pop is deaths per million. It's not per thousands or hundred thousands. It's actually deaths per million. So again, the error, the problem came about because the world site uses deaths per million for each state. On the other hand, most other people use deaths per 100,000, and also for most of the other variables, they used 100,000s or things per 100,000s. So I actually changed in the database the variable or created a new variable that was deaths per 100,000. But then a lot of times I still went back and used the death per million variable by my error. So all it does is put anything off by a factor of 10, really. It doesn't affect the interpretation of any of the analyses, but it does put things off by a factor of 10, and I apologize for that. But instead of changing all the slides, I'm just letting you know that whenever it says death pop, that's deaths per million, not per thousands or hundred thousands. And I thank you for your understanding with this issue. Okay, so I ran the process model just like our friend Field did. I went into the menus and I chose model 4. So you can see I chose model 4. Again, it took me a while to figure out where to put that model 4, but I chose model 4. Again, if you don't pick the right model, you're going to get errors. And I said the Y variable or outcome variable was deaths due to COVID. The X variable was density or population density. And the mediator variable was this air pollution variable. And of course, our sample size then is 50. So then again, we get our first piece of outcome, which we're going to sort of parallel the field analysis. So our outcome variable is air pollution, which is the mediator. Our predictor is density. So this is really the A path. You can see that there's a high correlation between population density and air pollution, 0.4078. Here's our R squared, our mean squared error, F, degrees of freedom. Our p-value is 0.0033. When we look at our model, our coefficient or our B coefficient is 1.6549. And now, I asked for standardized coefficients just because I was interested in them. So I did add in that I wanted the standardized coefficient here. Again, though, this is our unstandardized coefficient, standard error, t-value, associated p-value, 0.0033. Of course, it matches what's up here. And also, if we look at the R-square, population density explains about 17% of the variance in air pollution. Okay, then for the next analysis, we're going to be looking at deaths in the population as the outcome variable. And now we have in here two independent variables. Well, really an independent variable in the mediator. So the independent variable or the predictor variable is density. The mediator variable is air pollution. And we also have, of course, our constant in here. And so we can see that the constant significant again. Constant probably doesn't really matter all that much. We have our density data. And again, we can see that that is significant. So density is significant. And there's our associated unstandardized B or unstandardized B coefficient, the standard error, the t, the p-value, the confidence interval. And again, Field says interpret this confidence interval. If we look at the confidence interval, it doesn't include 0. Also, of course, air pollution, we want to see, does it predict deaths in the population? In fact, it does. And again, this is it. Both of these are after controlling for the other variable. So air pollution predicts deaths in the population after controlling for population density. The B coefficient, or the unstandardized coefficient, is 0.1432. You can see our standard error, our t, our p, it's significant. The p-value is 0.0078, which is below 0.05 and below 0.01. So we're okay there. So now we get to our direct effects and our indirect effects. I cut this off to make it fit, although we'll see what's on the next page. But I cut this off to make it fit. So you can see our direct effect. Our direct effect here is 0.6820. So again, our direct effect would be that part of the total effect that's due to the direct relationship between density and deaths after we control for air pollution. And then we have our indirect effect, which is 0.2370 for air pollution. And again, you can see this is significant when we look at the confidence intervals.